the challenge of keeping you entertained for even the last session, which is the most everybody's tired. So let me get through this. So this is mainly about machine learning, and it's not theoretical physics. And it's about a new paradigm. So most people are familiar with the notions of supervised learning, unsupervised learning, and clustering and so on. But these are things that we've seen for a long time. And there's a new emerging set of technologies coming from machine learning that I don't think many people are aware of, unless you're doing research in machine learning. And one of the most popular nowadays is called transfer learning. So I want to talk about it, hoping that at some point you might find use for this new set of technologies. Right? So what is the motivation for transfer learning, which is relatively new, and we're talking about the last 10 years, maybe 12 years in research in machine learning. And the idea is that now you should be able to transfer knowledge gathered from previous experience. So it's no longer the case that you apply a classification or clustering algorithm to certain data, and if you have more data, you have to start from scratch, and you have a new problem or a new task. Now, if the tasks are similar, let's say you're doing particle physics, and then you want to do classification as you were mentioning with your neural network, but now you switch to a different task similar to the previous one. Maybe it's a different particle or a different problem, but they're similar. Can you somehow save what you did before? Is there something you can rescue from the previous uses of machine learning? And that's the whole motivation of transfer learning. It has a lot of applications in the real world. Think about any kind of prediction where the model that you use has been used for many years, and now it's becoming obsolete. Say you're predicting a disease, but now there's new medical equipment and new sensors and new lab tests, right? And that changes the feature you're using to predict the disease. So what can you do to not waste all the things you learned from previous experience? Okay. So another name for transfer learning is that of learning to learn. And the idea now, the terminology we use is we have a previous task, we call it the source task, where the data was gathered, is the realization of certain source domain. And here it's what we're interested in. We have a new task, and the question is, what can we transfer from one domain to the other? Now, so the traditional approach to machine learning and classification is every time we have a problem, we run a learning algorithm, and then we generate a predictive model, right? Or in the case of unsupervised learning, we generate a set of clusters or density estimation. The new paradigm is now I have a set of previous domains, and from each of them I'm gathering certain knowledge that together with the new problem will lead to more accurate predictive models. And we've tried to use this in several astronomical problems. For example, we use it for classification of variable stars, long-period variable stars, making use of what we had before in the classification of Cepheid stars. And we showed that you always get better results if you exploit previous experience. And I'll talk about in more detail how this works. Right? And again, the motivation is that sometimes the data you have is outdated. Maybe you have now a new project, right, with a larger particle collider, which generates the data. The previous set of data has to somehow guide the generation of the new models. Transfer learning has also been used in an interesting way within the realm of neural networks. For example, in the classification of stars and galaxies, this could be seen as two different tasks. So on one hand, you can use a neural network to classify luminous objects from images, say, into different types of stars, assuming you know that all these luminous objects correspond to stars. And on the other hand, you can also use that for classifying galaxies, right? Well, it's been shown that if you do what is called multitask learning, where you have a longer neural network with the same input space or feature space, and we're assuming we're characterizing stars and galaxies in the same way from images. But you expand the output layer with as many classes you have when you combine both stars and galaxies. So now in the upper layer of the neural network, you have all possible types of stars and all possible types of galaxies. So as you train the neural network combining both the data set corresponding to stars and the one with galaxies, and you compare the performance with each of the individual models, you see a significant increase in performance. And the rationale is that there's some kind of patterns that you're gathering by training with both data sets that you were not able to gather when you were just dealing with one task alone.
So it classifies stars better
exactly.
rather than just distinguishing stars from galaxies.
Well,
the first thing you think of at the bottom is to distinguish.
Right.
You know,
right.
One bright blob from another bright blob.
Well, no. What would happen here in this combined neural network is that if you provide a star, right, with certain characteristics, it would accurately activate the node for the star, and it wouldn't activate the galaxy. And if you provide a galaxy, it would correctly classify the right galaxy. But because you're combining the two, you get better results. And so you're learning from one domain to do better on the other. Now, the exact theory is not understood yet. I mean, what exactly are the patterns that you're learning from one that you carry to the other one? That's still. But you look at the results and then you get better results. Other ways to use transfer learning are, for example, in a simple way, you can have a certain task where you learn certain parameters and time distribution, and then you use that as a basis to start looking for a new set of parameter values and a new time distribution for the time. And that speeds up things, makes it faster to get to a good model. We use that for classifying correctly landforms on planet Mars. And so we started with certain region for Isia valleys, which has a nice combination of craters and ridges and valleys. And so an expert would label some of those segments there with the right class label. And then we train that support vector machine, which is it's actually a very advanced type of machine learning model. I'm not sure if you're familiar, because what I've seen is that this is mostly concentrated on neural networks, but there's a huge gamma of other models that you can use, about 30 or 40 other models, and many of them could outperform neural networks. And so back to this problem, if we were to move to a different region that had a different distribution of craters and ridges and so on, we could use that initial set of coefficients to look for a better model, a good model, and that would speed up things considerably. So you don't have to start from scratch. And so we expanded that to many, many other regions. So on Mars, to get a full catalog of landforms, mainly 6 different types of landforms, including craters, ridges, and valleys, and so on. Okay, so that's the introduction to transfer learning. And there's a lot of theory and papers about that that I provide references about that. I wanted also to talk about a specific type of transfer learning that is becoming very popular recently, I would say the past 4 or 5 years, called domain adaptation. And maybe domain adaptation might find some practical use in particles. That would be interesting to see. Okay, so what is the difference between transfer learning and domain adaptation? Well, domain adaptation is one type of transfer learning, but it has certain peculiar characteristics that make it a problem of its own. We also have a source problem and a target problem, or task, right? But then now the new challenge with domain adaptation is that in the target task, the new task, you don't have labels. You lack labels. Okay, so you only have the class labels for the source task. Now that makes it very challenging, right? Because unless there's some real similarity between source and domain and the target task, you're in trouble. There's no way you can find a good model if you don't have any labels to train a neural network or the learning algorithm with that. Let me give you an example. Let's suppose these are positive and negative examples corresponding to a simple two-dimensional picture space. This corresponds to the source task, right? And when you run a simple learning algorithm, that you get a boundary, right? A model that says, well, whatever is above this linear boundary, it's going to be positive, otherwise it's going to be negative. Right? But here comes a new data set of which you ignore. You don't know the class labels. And the question is, well, what do you do? How do you exploit what you learned before? Now, the most naive way of proceeding would be, well, let's use the same model. And use the same model we had for the source task and apply it on the target. And you might find some errors. And that's because the new target domain has changed the distribution. Now you don't have maybe the same prior distribution or the posterior distribution of class variable and so on. So there's of course certain variations that you don't know about, but that are expected when you're dealing with a similar but not identical task. Right? So the way things work in domain adaptation is the following. You have a source domain, let's say a data set of particle collisions with all the characteristics for the different jets there, and the right labels for the particles. Right? So that's the source data. And now you have a new set of data, right, corresponding maybe to a different particle, and you want to test this idea. Maybe what I learned by predicting correctly that the previous particle can help me here, but I don't know yet. I don't have an expert yet helping me to classify this new particle. Right? So what we're going to do is use this domain adaptation technique, right, to compensate for the different distribution that is coming from the target domain, while at the same time exploiting what you learned before. And that would generate a new training set that would give you a new model. And now get some test data from the target domain that you didn't use for training and use that to come up with the right prediction. And so there are many reasons why the distribution for the target task is different. One of the most popular, because it simplifies things a lot, is to assume that there's simply being a change of density distribution. In other words, that the points can be found in a different region of the feature space. But other than that, things have remained the same. Right? Well, what you can do then is to generate a good model, right, that takes into account this change of distribution, is to start with the source domain, source task, the target task. You don't know the labels there, and give more importance to those examples in the source task that seem to be overlapping with the new distribution. That's the most simple thing. But just to give you an idea of how things can work. I mean, there are much more sophisticated ways. But I think this gives you a glimpse of one way of solving this problem. So if you were to train now with this new data set that expands what you had before, with these points that are labeled, and you generate a model there, you have a different boundary that hopefully now starts to do a better job at classifying the target task. So we found this a really very interesting, fascinating new approach to machine learning, because these kind of problems, you see them all over the place. I mentioned that there are more complicated ways of dealing with the domain adaptation problem. One of them, which I think is also very interesting, is one where you have certain source domains, right? Well, you have the source domain and the target domain, and then you're going to try to find a new space, a new feature representation that somehow puts the two together. Right? It finds a new representation where both distributions seem to overlap. And there are, again, mathematical ways of doing that. But that way of aligning both data sets has received a lot of attention lately in machine learning. Okay. Now, when the difference between the target domain and the source domain is huge, I mean, it's significant, and traditional methods to domain adaptation or transfer learning don't work well, one thing you can do is what is called active learning, another area that is mostly ignored by people outside machine learning, but that is very useful. Now, so let me talk to you about active learning. What active learning does is the following. You have a new domain, let's say the target task, and you don't know the labels, And what active learning is going to do is tell you what are those points, those instances in your new task that are the most relevant. That is, if you give me the label for those, I can come up with a new accurate model faster than if you slowly give me all the labels for all the points. Now, we're assuming that there is a cost for having an expert labeling instances, and you want to minimize that cost, which is something that is easy to understand, right? Because many times it's expensive to do. Now, there's been a lot of research on what does it mean, and how can you identify those instances that are the most relevant. And that definition varies among different approaches. But it's been shown that in practice, when you apply this, you gain a lot because you minimize the cost of having to classify many instances. For example, in the case of the Mars project, we applied active learning and we were able to have the expert label only a few hundred segments of an image rather than the millions he would have had to do to get labels for the whole image. So active learning is also something we were lately combining with domain adaptation to get better results in astronomical problems. Right? So again, we have just briefly to visualize how active learning works. Let's suppose we have a sample, right, from a certain distribution where we don't have the class labels. Randomly, at the beginning, we ask the expert to label some of them, which I'm showing here on start. We get the correct class labels, and we train an algorithm with those few examples. We get certain boundary, certain model. Now, one way of defining important instances, you could say, well, it will be those that have the lowest margin. Margin is the distance between each instance and the boundary. So look at those instances that have the lowest margin. Let's say the single one that has the lowest margin. Classify it, ask the expert to do that, and redefine your model. And so you can go on until you have converged to a stable solution. So now things get a little bit more complicated, but this architecture has shown very effective results. We had as before the source domain and the target domain with no labels. Domain adaptation is going to try to combine both the difference in distribution with the labels of the source data set, and active learning is also going to help us to get a few points in the target task with the correct labels. Okay. So we did, does this work, you might ask? Well, we did this for classifying supernova 1A, right? Why is this a good fit for the transfer learning and domain adaptation problem? Well, in the case of the supernovas, and this is true for many astronomical objects, there's two ways you can characterize luminous objects. You can either use spectroscopy, and that's very good, right? Because you have a lot of information from this object, including the chemical composition and the redshift, and it's all very accurate. The problem is that this is very expensive. It takes a long time, and we're unable to apply a spectroscopic analysis to the massive amount of luminous objects that the new surveys are gathering these days. Okay. Instead, we have what is called photometric analysis, right? It's less accurate, has lower resolution. It's more of a summarization of the intensity of the electromagnetic radiation, but it's cheap, and most modern surveys are based on photometric analysis. So here we have the new task. We have a big sample of luminous objects, or let's say supernovas, but we want to distinguish supernovas 1A from not 1A. And we don't have the class labels. We don't want to ask experts to do this classification using spectroscopy because it's very expensive. On the other hand, we have reasonably high, big previous data set that corresponded to this analysis using spectroscopy. This could be considered as the source task, and you use the task.
You know, photometry on the switch also has the classification.
Oh, you can do that, right?
No, I mean, do you in practice?
So in practice nowadays, if you want to know exactly what is a redshift and chemical composition, you have to do that. But it's impossible. I mean, the amount of luminous objects being gathered with these new surveys is just outpacing the.
No, I understand getting spectroscopy to the bottom is hard, but you already have photometry.
Right, exactly. Oh, here, yes,
Yeah,
we do.
okay.
Yes, we do have photometry. Although the input space is the same, so that's not a problem. So again, we want to automate the classification of supernovae, 1A using training data as the training data, the spectroscopic analysis, test data, the photometric analysis. And there's a different distribution. Normally, the training set corresponding to spectroscopic analysis corresponds to brighter nearby objects. That's why we can do that. Except deeper surveys doing photometry, correspond to farther galaxies or stars that are farther away, and so you see a different type of region in the instant space feature space that is populated by the target stars. So the question is, how can we take advantage of existing supernova data sets to classify the new photometric surveys? So that's a good fit for transfer learning. Right? So we did this study. We had simulated data coming from the Supernovae Photometric Classification Challenge, mimicking the characteristics of dark energy survey data. So there's more specifications about the data itself, but essentially we have this distinction between the two sources. Right? We initially did some dimensionality reduction to avoid having the cursor dimensionality and having to deal with too many features. From 108 features, essentially capturing the type of light curves, we went all the way down to 20 features using kernel principal component analysis, which is a variation of principal component analysis that it's actually very effective. And we also used a bit of active learning, right, to make sure we had some instances labeled from the target distribution. And so when we measured both accuracy, which is the proportion of stars correctly classified as supernova 1A, and purity, focusing only on supernova 1A and how many of them were correctly classified, we observed an increase, significant gain in performance, especially as we increase the number of examples labeled by experts using the active learning part. Right? And in fact, some domain adaptation techniques were really bad, especially the one that was trying to find a new space that merged the source and test domain, because the distributions were completely different. All right, that was basically.
Thank you for this wonderful introduction to a field that I think few of us are familiar with. I expect there was a question. Oh.
Okay, one thing that occurred to me all during the talk for particle physics, rather than, we don't have that many new particles, sadly, but we will simulate all sorts of particles. So you have a simulation change, say, the energy region jets, parameters in the model beyond the standard model that generates it.
Yep, absolutely. That would be one case where you would have a good fit for the transfer learning problem.
So simulation in general.
And simulation in general.
They go on forever.
Yes, and people are just starting to jump into that.
Right. It seems to us to be able to learn simulation.
Right. Right, but simulations are expensive, so if you learn, right, that's not the idea. Right. If you learn to predict what will be the output of a simulation, then you can expedite the process. In fact, I remember hearing the talk of an astronomer from Chile, and he said they had a simulation of a certain telescope It took them 2 years to come up, bring the software running well with this simulation. And they used, on the other hand, machine learning to predict the output, right, of the simulation, and they got better results. So the guys said, just forget about simulation, just use machine learning. So yeah, that would be one thing.
Okay, if there are no other questions, and I still have one. What is if the my impression is that you are assuming that the source and the target model are sort of similar, but you don't know. So what happens if there's some qualitative change? I mean, like in the disease case, like you have these new lab tests or something, and all of a sudden the picture changes. You understand the way of infection or something like that.
Right.
Would you? I mean, how much bias is there? How much does the old model pull you towards the old results and not give you the new results? What is the threshold to jump over?
Right. That's actually a very good question, because in practice that happens, right? And so while this theory of domain adaptation and transfer learning was being developed, all the papers I remember reading about were saying, we are assuming there's a similarity in distribution, and that's it. I mean, there's nothing more to it. But when we started using this in practice, you would see that in some cases the distribution is so different that it doesn't apply anymore. So what people are doing now is doing the following: doing domain adaptation and active learning at the same time. And if the distributions are very different, slowly the domain adaptation is going to be pushed aside, and you're going to rely more on the active learning, which is really telling you something about the true distribution. But if the two distributions are overlapping or similar, then you start to rely more. And people have suggested more like a Bayesian approach, where the prior is coming from the source domain, but the new data, the likelihood, is telling you how much you should deviate from your source prior or rely on it.
Okay, I think then we're done for this session. So I think there is still one more talk in the other sessions, but otherwise I think we will meet back for the drinks. Okay, thank God.